And now for something completely different. Talk about chemical reactions. The nice thing about this is there's almost no math in it. There's a little bit of counting. Yeah, nice? We don't need the calculators right now. Okay, so we've talked about chemical changes, right? In a chemical change, the substances change. A chemical reaction is a chemical change. Your original substances are destroyed and new substances are formed. What happens is that the atoms are rearranged. It's like building with Lego blocks. And you have a little man and a little tree, and you take those apart and you put them back together, and now it's a house or something. The numbers of Lego blocks of each type are the same. We're just rearranging them. The atoms are the same. We're just rearranging them. So we use a chemical equation to describe the chemical reaction. We have a very particular way we write it out so that everybody who understands chemical reactions looks at it and understands exactly what we mean. So it's just a shorthand. What we do is we start with the reactants on the left and an arrow that's pointing to the products. So just like we read from left to right, we're writing this equation and representing that it's starting on the left and going to the right. The reactants react to produce the products. So reactants on the left, products on the right. From these equations, we're going to have the following information: formulas and states of reactants and products, relative numbers of reactant and product molecules, and we can use these equations to figure out masses. This is a real practical kind of a deal. So maybe you're synthesizing ethanol in a factory, right? And you've got your starting ingredients, and you need to make 50,000 kilograms of ethanol. You need to know how much of your starting ingredients to put in there so that you get the right amount out. Yes?
This is kind of off topic, but not really. But on the chemistry lab online stuff, when it says like the tutorials, does that go over all the definitions? Like basically your YouTube videos? Is that what it is?
The tutorials in Mastering Chemistry are for practice in my class, and I would encourage you, if you're struggling at all, to go and look at those, because they're going to have you doing some problems, but they're going to give you a lot more information. They're going to be different than my lectures, but they're covering topics from the lectures.
Okay.
Yeah. So if you haven't looked at the tutorials, I would encourage you to go and look at them. It's a great way to practice. I mean, you can study smart or you can study hard, right? So studying smart and getting the most points for your efforts, if you go and you look at the homework and you're like, I don't know, maybe you should go find the tutorial that is similar or on the same topic. Work your way through that where you can make all the mistakes you want with no penalty. Figure it out over there. Now come over and do the homework assignment that is worth points. These are the states of reactants: gas, liquid, and solid. Those are the same states of matter that we've talked about, and so the abbreviations are pretty simple. It's just the first letter of the word. And then we have AQ. AQ stands for aqueous, meaning it's a water solution. It's dissolved in water. Let's look at the combustion of methane. Methane is the primary gas in natural gas, and when it burns, it produces carbon dioxide gas and water in the gas state. Now, water is a liquid at room temperature, but when natural gas burns, it's hot, right? And so that's why, in your gas stove at home, you don't see water puddling up around it, because it's coming out in the gas state and it just floats into the air. So we could write an equation like this. Here's the formula for methane, which you have no way of knowing yet. We're just sharing it with you. CH4 in the gas state, reacting with oxygen in the gas state. Why is this O2? It's one of the diatomic elements. So horses need oats for clear brown eyes. The oats, oxygen. And this is where we need to know things like that. When one of those 7 elements is by itself, the formula has a 2. Here's the arrow that represents the words to produce. Here we have the formula for carbon dioxide. It says it was a gas, and water, gas. But this isn't quite right. Here we have 2 oxygen atoms, and over on the right side, there are 2 oxygen atoms here, and there's 1 oxygen atom there. So we started with 2 oxygen atoms, and we end up with 3 oxygen atoms. Is that possible? Can you create oxygen atoms in a chemical reaction? No, you can't. So that's not good. There's another thing not good about this one, the hydrogens. Over here, you've got 4 hydrogen atoms in 1 molecule of methane. And over here, we have 2 hydrogen atoms in this molecule of water. What happened to the 2 hydrogen atoms? Destroyed. Is that possible? No. Maybe they got turned into the oxygen atom. You think that happened? No. Matter's not being created or destroyed, and elements don't convert from one to another in a chemical reaction. This is not a nuclear reaction. So that's not happening. The problem is our equation isn't quite right.
So that's what nuclear is?
A nuclear reaction involves changes in the nucleus. And in order to change what an element is, you have to change the number of protons. So chemical reaction, electrons are doing stuff, but the nuclei of all the atoms stays the same. So if it starts out a hydrogen atom, it remains a hydrogen atom. It doesn't change into anything. So this equation is violating the law of conservation of mass. So we can't have that. So what we do is we balance the equation. So let's look at the pictures down here. So this is a space-filling model of this molecule. There's 1 black ball and 4 white balls. And here we have oxygen, 2 red balls, right? And here's CO2, and there's water. My pointer. There we go. So if you think about these as round Lego blocks, I'm going to need 2 of these oxygen molecules so that when I take this thing apart, I can put 2 oxygens on that black carbon, and then I have 2 more oxygens. One will take care of 2 of the hydrogens, and the other will take care of the other 2 hydrogens. And so I end up with 2 water molecules. It's very important to grasp the visualization of this equation and what's going on. We're taking these, pulling them apart just like they were little building blocks, and putting them back together. Of course, it's more complicated as to why they would do that, but in terms of writing a chemical equation, that's all we need to think about. Anybody have any questions? We can't change the formula. If we put O4 here, then it would be balanced. We'd have the right number of oxygen atoms. But does oxygen make a molecule with 4 atoms? No, it doesn't. So we need 2 of these units. And over here, we observe from these reactions, that's where we're getting the products. It's been observed. It forms water. Water is H2O. You can't change the formulas. So when we balance the equation, what we're going to do is we're going to change the number of molecules. We can say, well, there must have been 2 oxygen molecules to react with this 1. And over here, then, we must produce 2 water molecules. We only produce 1 carbon dioxide molecule. Any questions? Yes? Like at the bottom? No, this is not a chemical equation down here, really. This is just kind of summarizing what we've got going on up there. So they're saying the total is 1 carbon, 4 hydrogens, 4 oxygens on this side that we started with, and 1 carbon, 4 hydrogens, 4 oxygens that we end up with. So same number of pieces of each color. Okay? These are the steps for balancing chemical equations. And writing and balancing chemical equations is an important part of chemistry. We're going to get through this balancing thing and then we'll stop. So first we write a skeleton equation, just showing the formulas for the reactants and the formulas for the products. And then we look at it and we figure out what's missing and we add in coefficients so that we get it balanced. This is called balancing by inspection, meaning we're looking at it and we're balancing it. There's some guidelines, like they're saying that you should balance atoms in the more complicated substances first and leave the elements for the end. That usually makes it more simple. What I tell students is you can start anywhere you want, and if it seems like it's not going well, start over and start with a different element, and usually that fixes the problem. It's possible to end up with coefficient fractions at the end. If you do, then we need to get rid of them by multiplying by the denominator, multiplying all the way across, and then finally we need to check and make sure that we're got everything right. And this thing at the bottom, this is the checking on that one.
This case?
Yes?
On your last example for the oxygen, doesn't it have three oxygens on the right side compared to
You mean on this
the number,
equation?
the number of oxygens?
Well, this one has 2 oxygens, and this one each has 1 oxygen, but there's 2 of those molecules.
Oh, okay.
Okay? It takes a while before you can look at the letters and numbers and really grasp what they're meaning. So when I see 2 water, I think of that being like 2 bicycles, where the oxygen is the frame and the hydrogens are the wheels. In a very simple form, a bicycle is 2 things, wheels and a frame, right? So if I have 2 bicycles, I have 2 frames and 4 wheels. I haven't met anyone who has trouble with that idea. We can grasp that. You can picture a bicycle. Water is just like that. For every oxygen, there's 2 hydrogens. So you got to work through it until it starts to make sense and keep asking questions. So let's do an example. In these examples, they force us to practice our nomenclature. Isn't that thoughtful of them? Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. The first step is we need to get some formulas. When we look at this, the reaction between, so we've got solid silicon dioxide and, that's the plus sign, and let's make that, maybe if we do, so that's our, ooh, that was really fat, maybe a little too fat. That's the plus sign, and solid carbon to produce. That's the arrow. Solid silicon carbide and carbon monoxide gas. Okay, so we got the sentence, and we need to translate it. Silicon dioxide. SiO2. Very good. That is a molecular compound, and the prefix di tells us there's 2 oxygens. The sentence tells us it's a solid, so I put S in parentheses afterwards to indicate it's a solid. And I'm going to leave a little space here in case I need to put in a coefficient. Solid carbon. That's an element. It's just C. And it's a solid. Anytime you have an element, and you can recognize the elements because they're one name, don't get fooled, water's not an element, even though there is a W in the periodic table. Always ask yourself, is it one of the 7 diatomic elements? It is not. So it's just C. To produce solid silicon carbide. S-I-C. Are there any sick? Yeah, sick'em. That's what you tell the dog. Are there any prefixes in that? No. It's a little disturbing, isn't it? Because when we learned about molecular nomenclature, we would have said silicon monocarbide, right? But silicon is a semi-metal on the non-metal side of the stair-step line, and carbon is on the non-metal side. So for nomenclature, we have two nonmetals. It's got to be a molecular compound. The absence of the mono should not disturb us too much because chemists are dropping ones all over the place, right? And so we sometimes drop the mono on the second element too. So if you see that, don't be alarmed, but don't do it yourself. Okay? So anyway, it is SiC, and we're told it's a solid. So there's an S there. And leave a space. Carbon monoxide. CO. The mono tells us only one oxygen, and that's a gas. Everybody okay with this so far? Now we need to look at this and see what we have. So I'm going to show you what I call the tally method for balancing equations. And I'm just going to do this one, and then we'll do the other examples next week. So one way to approach these is to draw a vertical line at the arrow to make it clear where's the beginning, where's the end. We're starting over here and we're going over there. We need the stuff on each side of that line to be equal. And then I'm going to make a list on this left side of the different elements. I'm just going to go in order as I run into them: silicon, oxygen, and carbon. And I'm going to take inventory first so I know what I've got. It's a little bit silly because this is a very simple equation, but it's a technique that will be useful. So I look at this first formula, SiO2, and I ask myself, how many silicon atoms in the formula? So I put a 1 here. And how many oxygens? There's 2. And how many carbons? None. 0. And then over here, carbon. Well, there's no silicon and no oxygen and 1 carbon. I'm doing each compound separately. There's a reason for that. And so here I've got 1 silicon, no oxygen, 1 carbon, no silicon, 1 oxygen, 1 carbon. Everybody okay with that? I took inventory. Now we're going to compare the right and the left side of the line. So I look at silicon, and the total here of 1 plus 0 is 1. And on the right side, 1 plus 0 is 1. Awesome. Cool. Oxygen, 2 plus 0 is 2, and 0 plus 1 is 1. There's not enough oxygens over here. This is the only compound that has oxygen, and somehow I need to double it. So if I put a 2 in front of CO, that will double the number of oxygens. But it changes the other things as well. It changes the other 2. Because if you have, this would be a unicycle, I guess. If you have 2 unicycles, you have 2 seats and 2 wheels, right? 1 on each. The 0 doesn't matter because you can multiply that by anything you want and it's still 0. Did I change anything in the silicon row? No, so I don't have to worry about that. So I've got silicon done, I've got oxygen done, and now I'm going to look at carbon. On the left, I have 1 carbon. On the right, I have 3 carbons. So I need to put a 3 in front of this one, and that will change this to a 3 nicely without changing either of those. So there's our balanced chemical equation. To check it, I'm going to look at this again and say, okay, well, how many silicons on this side? There's 1 here, just the 1. And over here, just the 1. Okay, cool. How many oxygens? 2 there and none. Okay, just 2. No oxygens. 2 oxygens. Very nice. No carbons. 3 carbons. There's 1 carbon and 2 more 3. That's what you do when you check it. Any questions? Yes?
So say the carbon on the left side, it could also, say it was carbon monoxide, keep going until...
Yeah, so what if in changing this, you also change the oxygen? Then you'd have to go back and balance the oxygens again. And then sometimes that would change something else. And then if you come back and you're realizing that you're going in circles, it's like, okay, I changed the carbon and that made me change these other things, but now I'm back at changing the carbon again. Hey, wait a minute, what's going on? There's 2 things you can do. The first thing is make sure that your formulas are correct. okay? When you're doing homework or labs or stuff like that, you have the internet in your pocket if you have a smartphone, right? So don't use Google initially to write the formulas, but check them. Make sure that you did them right before you go on and balance everything. The other thing, if your formulas are correct and you're still spinning your wheels, go back and start with a different compound. I have found that most of the equations that are given in general chemistry, if you just start on the left and go across in the order, they're usually okay. But it worked out that this element was last. The reason you want to leave the element for last is because we got everything else fixed up, and then when we adjust the element, it doesn't mess anything else up. Any other questions? So you're going to have to do some practice and make some mistakes and ask me some questions. I've been getting alarmingly few text messages. I love it when students text me with questions. I'm sitting at the basketball game. Somebody wants to know, the difference between this and that. And it's interesting to me. So don't hesitate, okay? We'll finish the rest of this next week.